Today we will present our research on the recovery of silicon from decommissioned solar panel, proposing as an anode material for lithium-ion batteries.
Nowadays, both globally and in Vietnam, we are witnessing the widespread adoption of solar panels as a green energy source. Solar panels typically last approximately 20 to 25 years. At the end of their life cycle, they are collected for recycling to utilize a valuable material, especially silicon. However, for recycling silicon to reuse in new solar cells is highly complex, requiring large amounts of toxic chemicals to remove the impurities and to restore the crystal structure. However, silicon can use as a nanomaterial for lithium-ion battery with theoretical capacity of up to 4,200 mAh per gram, which is 10 times as high as conventional graphite anodes. And for this application, silicon does not require high crystallinity and also can even benefit from the remaining impurities. As a result, the cost for the refinement process, which is accounting for about 70% of total cost, can be reduced significantly. Drawing from this practical background, our team has chosen the topic, the research on the recovery of silicon from decommissioned solar panel for repurposing as a nanomaterial for lithium-ion batteries. The main focus of our research was to explore the potential of silicon as a high-performance anode material.
Despite high capacity, silicon suffers from severe volume expansion during lithiation, which leads to structural collapse and rapid capacity fading. To address this issue, graphite, a low-dimensional material with superior electrical conductivity and excellent mechanical properties, was introduced to enhance electro durability. From this perspective, the project aimed to address two main research questions. First, can the silicon be recovered and refined from decommissioned solar panel using a simple, low-cost, and environmentally friendly process for using as an anode material for lithium-ion batteries? Second, can the electrochemical properties of the silicon be effectively improved by forming a composite with graphene? To answer this question, four specific result objectives were defined. First, to develop a simple process to refining silicon recovered from decommissioned solar panel. Second, to investigate in the electrochemical properties of the silicon and evaluate its feasibility in lithium-ion batteries. Third, to fabricate a composite from silicon and graphene to enhance the electrochemical performance. And finally, to assemble a prototype of lithium-ion batteries using silicon graphene anode and commercial LFP cathodes.
Based on these objectives, our research process is as follows. First, silicon was recovered from the end-of-life solar panels with a physical separation in section 2.1, followed by refinement process using acid and alkaline solution and hence with sonication. The silicon sample before and after refinement process was analyzed and compared using EDX, XRD, and SEM techniques. And to improve the electrochemical properties, a silicon graphene composite was synthesized via high-energy ball moulding. The electrodes and half cells was fabricated in a standard process in section 2.3, while the electrochemical properties was analyzed using GCD. The specific capacity and life cycle was evaluated using GCD.
The chemical composition of the silicon was analyzed by EDX. The aluminum, which was the main impurities of the silicon, has been removed effectively after refinement, leaving primarily silicon and oxygen. The XRD analysis indicates that the refinement silicon exhibits an amorphous structure, and the SEM image in figure 3.4 and 3.5 reveals that the particle morphology of silicon stay nearly unchanged after refinement, with particle size ranging from approximately 5 to 50 micrometers. For the composite silicon graphene materials, the SEM image shows that the particle silicon has been uniformly decorated with graphene sheets on their surface, and the EDX mapping confirms the homogeneous distribution of silicon, carbon, and oxygen throughout their materials. The electrochemical properties results are the core finding of this study. The CV curves in figure 3.8 display distinct cathodic and anodic peaks with corresponding to reversible lithiation and delithiation process, demonstrating the rechargeability of the material. From the GCD results, the initial capacity of the silicon reached approximately 1,600 milliampere hours per gram. However, rapid capacity fading occurs, and the electrode fails after only 50 cycles. This indicates that silicon can function as an anode material for lithium-ion batteries. However, its durability still remain limited.
To overcome this limitation, a silicon graphene composite was evaluated. CV measurements in picture 3.10 shows a similar oxidation and reduction peaks to those of silicon. And the composite has a specific capacity of around 600 mAh per gram and can show a stable performance over 100 cycles, demonstrating an improvement in the stability compared to pure silicon. Subsequently, a fuel cell was assembled using this composite and LFP cathode. Charging in each charging at 0.5 C in picture 3.12 shows a stable performance over 50 cycles, and the battery can also power a common lab, highlighting its practical application potential. This research has achieved its objectives. First, successfully develop a process to recover and refine silicon from end-of-life solar panels, achieving cost saving at least 50%. Second, successfully evaluated electrochemical properties of silicon after refinement process. Third, successfully fabricated a convert silicon graphene composite, demonstrating an improvement in stability. And fourth, a prototype of lithium-ion battery was assembled using silicon graphene composite and LFP cathode, demonstrating a practical application potential.
After completing these objectives, there are several future directions are proposed. First, to optimization the silicon to graphene ratio in the composite system. Second, to investigate in the alternative electrode protection strategies, such as the core shell structures or the polymer coating layers, to further enhance the electrode durability. And finally, to simultaneously optimize the balance between the economic efficiency and the environment needs throughout the fabrication and refinement process. Ủa, bị dừng quay này chưa à?